Good afternoon, everybody. Hope you're all healthy and safe at home. So, we are going to continue our section 1.4. In the previous lecture, we had discussed about what is meant by seminorms. So, basically, seminorm is a function p from E to R plus which satisfies the three properties. The first one is it is given in the text, it is p of 0 is 0. That is, in case of norm, we had defined that p of x is equal to, or norm of x is 0 if and only if x is 0. Okay, so this in this semi-norm, what is the condition? The condition is p of x is greater than or equal to 0. It is always non-negative, and it need not be that it is 0 only for x is 0. It can be 0 for any other values also. So that is the definition of the semi-norm. So the three properties are that p of x is greater than or equal to 0, p of lambda x is equal to modulus of lambda into p of x, and p of x plus y is less than or equal to p of x plus p of y. And in the end of the last lecture, I had asked you guys to check whether the kernel of this semi-norm is a subspace or not. So what will be the kernel? In our textbook, it is denoted by E dot. That is, E dot will be the set of all x in E such that p of x is 0. That is the kernel of the function p. So I had asked you to verify whether this E dot is a subspace or it is a subspace or not. So I hope you guys have verified it. Now next, what we are going to show is that we are going to show that p of x plus y is independent of y element of E dot. That is, whenever we are taking an element y from E dot, that is the kernel, we are going to show that p of x plus y will be independent of that particular element. So let's see how we can prove that. So we are given y element of E dot, right? So if y is an element of E dot, by definition of E dot, what do we have? P of y will be equal to 0. Now, to show that it is independent, the function p is independent, let us consider two elements, y1 and y2, both element of E dot. So by definition, we have p of y1 equal to 0 and p of y2 equal to 0. Now, consider p of x plus y1. Okay. This can be written as p of x plus y1 plus y2 minus y2. That is adding and subtracting y2. Now, let us see. This can be written as less than or equal to p of x plus, I am taking y2 plus p of y1 minus y2 by using the third property of the semi-norm. So what we have got, we have obtained that p of x plus y1 is less than or equal to p of x plus y2 plus p of y1 minus y2. Right? Now in this portion, we are going to again apply the third property of the function p. So what do we get? X plus y2 plus p of y1 plus p of minus y2. So by the second property, minus y2, we can take minus sign common and it will be the magnitude. So it is nothing other than p of y2 itself. Now what is the value of p of y1 and y2? Since y1 and y2 are elements of E dot, they are equal to 0. So we get p of x plus y1 is less than or equal to p of x plus y2. Now, in a similar manner, we can show that p of x plus y2 is less than or equal to p of x plus y1. In the same way that we did just now, we can show this inequality also. So, using the two inequalities, what do we get? We get p of x plus y1 is less than or equal to p of x plus y2 is less than or equal to p of x plus y1. So this implies, what do we get? P of x plus y1 is same as p of x plus y2. So whatever be y1 and y2, since they are elements of E dot, we can show that P of x plus y1 is equal to P of x plus y2. So we can conclude that P of x plus y will be independent of y whenever y is an element of E dot. Now, so we can consider P as a function on the cosets. P of coset x is equal to P of x. That is, whenever we are writing the term coset of x is basically set of all x plus y, where y belongs to that E dot, the subspace. So we stated just now that y will be, the function P will be independent of this particular y element of E dot. So we can consider the function P as a function on the cosets. So we can state that a semi-norm P of x on E defines naturally a norm on the quotient space E by E dot. So I hope it's clear. We just now proved that the function, the semi-norm P, is independent of y whenever y is an element of E dot. So we can consider that function as the function, or that semi-norm as the norm on the quotient space E by E dot. Now, when we consider the space LP, we had defined, or we had given a norm by norm P of x is equal to summation mod xi whole raised to p whole raised to 1 by p. In a similar manner, we can give a functional analog of the LP space, and we are considering the space of continuous functions Cp of AB. That are all continuous functions on the closed interval AB. And the norm is norm P of f is equal to integral e to b mod f of x whole raised to p whole dx whole raised to 1 by p. Instead of summation from I equal to 1 to infinity, we have integral a to b. That is the only difference. So you can check whether this norm is satisfies all the three properties. So next we can move on to the last section of our this first chapter, that is section 1.5, and in this section we are going to basically discuss about the completeness of a norm space. So before going to the definition of a complete norm space, we will first recall what is the definition of a Cauchy sequence. I know that you guys are familiar with these terms, but let's just rewind with our memories. So let's see. What is a Cauchy sequence? A sequence xn in the space X is called a Cauchy sequence if and only if for every epsilon greater than 0 there exists a capital N such that norm of xn minus xm is less than epsilon for every n comma m greater than n. Okay, or in other words, we can say that norm of xn minus xm tends to 0 as n greater than m tends to infinity. So that is the definition of a Cauchy sequence. What is it? A sequence is said to be Cauchy if for every epsilon greater than 0 we can find a capital N such that norm of xn minus xm is less than epsilon for all n comma m greater than n. Now, by the definition of Cauchy sequence, we can easily understand two properties of Cauchy sequence. The first property is that the limit n tends to infinity, norm xn will exist whenever the sequence is Cauchy. So let's see how we can do that. We need to show that the limit of norm of xn exists. So what is given to us? We are given that xn is a, suppose xn is a Cauchy sequence. Okay, xn is Cauchy sequence. Then we need to show that limit n tends to infinity, norm xn exists. Okay, so we have seen the inequality that modulus of norm xn minus norm xm will be less than or equal to norm of xn minus xm. We have used the same inequality to show that the norm is continuous. So we have seen that modulus norm xn minus norm xm is less than or equal to norm of xn minus xm. Now since xn is Cauchy, this xn minus xm will tend to 0 for any suitable n. It will tend to 0 where n greater than m tends to infinity, right? So we get modulus of xn norm xn minus norm xm is tending to 0. So what can we say? We can say that the sequence norm xn will be Cauchy's, right? Will be Cauchy's. So since this is Cauchy's, and what is norm basically? Norm is a function from the space to set of real numbers, right? Now we know that R is complete. Since set of real numbers is complete, norm of x as an element in R. So if we say that in R norm xn is Cauchy's, we can also conclude that norm xn will be convergent. Okay, so if norm xn is convergent, its limit must exist. So I hope that is clear. The first property that we can obtain from a Cauchy sequence is that if xn is a Cauchy sequence, then limit of norm xn will exist, or norm xn will be a convergent sequence. The proof is very simple and it is clear. Now let's move on to the next property of which is obtained from this Cauchy sequence. Let's see. The second one is that if xn is a Cauchy sequence, then it will be a bounded sequence. How can we say that? We can say that xn norm xn, we showed that in the first property that if xn is Cauchy's, then norm xn is convergent. Okay, and every convergent sequence will be a bounded also. So if norm xn is bounded, then we can find an capital M such that norm xn is less than equal to M for all n belongs to n, and thus we can say that xn is bounded. So what were the two properties that we showed? We showed that whenever xn is Cauchy's, limit norm xn will exist, and as limit norm xn exists, norm xn sequence norm xn will be convergent, and convergent sequences are bounded. So from that we can also conclude that the sequence xn will be bounded. So now let's see what is meant by the complete space. Okay, a normed space X is called complete if and only if every Cauchy sequence in that space, every Cauchy sequence xn in X converges to an element X of the space. Okay, a normed space is said to be complete if every Cauchy sequence is convergent. The converse part is that is every convergent sequence will always be Cauchy. So you can verify that. If every Cauchy sequence is also convergent, then we can conclude that the norm space is complete. And some examples are given, that is R with modulus and C with modulus are all complete spaces. R and C and these are all complete spaces. But whereas when we come to the irrational case, that is Q, rational numbers and irrational numbers, they need not be complete. So next we'll define what is a complete norm space. That is, we just now stated that a complete norm space will be complete if and only if every Cauchy sequence is convergent, and a complete normed space, that is the tuple X along with that norm, is called a Banach space. So from now on we won't define, or we won't be using the term complete norm space. Instead of complete norm space, we will be using the term Banach spaces. So with that said, in the next section we can discuss what are the few examples of the Banach space. So that's it for today's section. So thank you. Stay home and stay safe.